It's kind of wild, how some ideas in tech just become like gospel, almost like unquestionable truths. Take normalization layers in neural networks, for example.
Yeah, I see what you mean.
Back in 2015, batch normalization, that was huge, right? A game changer.
Definitely felt like a big leap forward.
And then, of course, layer norm, like essential for transformers and all that followed. And since then, it's like all the exciting stuff, all the innovation has been in, I don't know, attention mechanisms or convolutions.
Right, right.
But normalization kind of just been there, chugging along, almost taken for granted.
It's true. The assumption has been you need these layers. Like they're fundamental for training deep networks, period. They make things stable, they help the training go faster, and ultimately you get better performance. So to even question that they might not be absolutely necessary is, well, it's a pretty big deal.
And that's exactly what makes this paper you sent me so fascinating, so ripe for a deep dive. This Transformers Without Normalization study, brand new, just out this March. It really throws down the gauntlet, doesn't it?
It does. And that's exactly what we're going to unpack today. Can transformers work without normalization? Not just work, but maybe even work better. That's the core question here.
And the paper offers up a solution, a pretty, dare I say, simple one.
Yeah, you could see that.
Dynamic Tanh, or DYT. When I saw the formula DYTX, Tanh, honestly, my first reaction was, wait, that's it? It seems almost too straightforward to replace something as, well, as intricate as normalization.
The elegance is in the simplicity, I think. The researchers, they look at what layer normalization was actually doing in transformers in practice. And they noticed a pattern, this kind of tan-like behavior, these S-shaped curves between the input and output activations. Like it was both scaling things and squashing those extreme values.
So DYT, if I'm getting this right, it's mimicking that observed effect, but without all the heavy statistical lifting that normalization usually does.
Precisely. It's about achieving similar scaling and squashing, but through this element-wise operation. No need to calculate the mean and variance of the activations like traditional methods do.
And the results they got, it's pretty impressive stuff. Transformers with DYT performing as well as, sometimes even better than, their normalized counterparts. And we're talking across the board. Image recognition, text generation, supervised, self-supervised learning, computer vision, massive language models, often without even needing to tweak the usual hyperparameters.
And that's what makes this so potentially groundbreaking. If this holds up, if it's as robust as it seems, it really makes us rethink what we know about normalization in deep networks. Could mean faster training, faster inference, especially for those huge cutting-edge models that are getting bigger by the day. Think about the implications of that.
No kidding. Okay, before we get too far ahead of ourselves, let's rewind a bit.
Sure.
Back to basics. Normalization layers, just a quick refresher so everyone's on the same page. What are they, really?
Right, so most of them, they follow a pretty standard formula. You've got your input data, you subtract the mean value of that data, then divide by the standard deviation. You add a tiny constant in there to avoid any divide by zero issues, just for stability. And then you scale and shift the result using learnable parameters, usually called gamma and beta. So the formula looks something like this. Normalization, x plus x plus.
Okay, got it. So the difference between all these different types of normalization, it's really about how they calculate that mean and variance, right?
Bingo. Batch normalization, the OG, the one that really kicked things off, that calculates these statistics across the whole batch of data you're feeding in, and also across each element or token within that data. It's been super effective, especially for CNNs, convolutional neural nets, the kind used for image processing. But for transformers, it's mostly layer normalization, or LN, and root mean square normalization, RMS norm, that are in the spotlight.
So LN, that calculates the mean and variance for each individual element, each token in a piece of data, right? Basically normalizing each input independently across its features.
Yep, that's a good way to think about it. And RMS norm, it simplifies things even further, skips the whole subtracting the mean step, and just normalizes by dividing by the root mean square of the values. The paper does mention that the transformer architectures they looked at, most of them used LN. LAM-MA was the outlier using RMS norm.
Okay, good refresher. Now, they did something really interesting in this paper. They analyzed what these normalization layers actually do inside trained networks. How do they even go about that?
Well, they took some pre-trained models, high performers, a vision transformer, or VIT for image tasks, Wave2Vec 2.0 for speech processing, and a diffusion transformer, DIT, for generating images. All of these were originally trained with LN.
So they basically just ran some data through these networks and watched what happened.
More or less. They focused on the LN layers. specifically what was happening right before and after the normalization itself, the subtracting the mean, dividing by standard deviation part. But before those final learnable parameters, the gamma and beta came into play. And since ln doesn't change the shape of the data, they could directly compare each input value to its corresponding output.
And that's where they saw the tan thing, right? Especially in the deeper layers of the network.
You got it. And this is where it gets cool. Look at figure 2 in the paper. You'll see it clearly. The ln layers, deeper in the network, they showed these S-shaped curves when they plotted the input against the output. That shape, it's super close to a hyperbolic tangent function, a tan function. The earlier layers, they were more linear, but even those could be kind of approximated by the middle part of a tan curve.
And that's pretty surprising given that ln itself is doing a linear operation on each individual element. How does that per element linearity become this overall nonlinear thing?
It's all about the interplay, really. Even though ln's doing a linear transformation for each token, each of those tokens has its own calculated mean and variance. So zoom out, look at the whole picture, all those activation values together, that per token linearity goes out the window. What you get is this emergent nonlinear transformation, and boom, it looks a lot like a scaled tan function.
And they also saw this squashing effect, right, on those values that were way bigger or smaller than the average.
Absolutely. They noticed that for those outliers, the normalization was mainly pulling them in, making them more like the rest of the pack. Their hypothesis is that this squashing, this nonlinear squashing, it's actually crucial. It keeps things stable during training, prevents the activations from going haywire, getting too big or too small. And what's really interesting is that most of the data points, they fell in a pretty linear range. It was those outliers, those at the edges, that got the most dramatic makeover from normalization.
It's like normalization is the bouncer at the club, keeping the riffraff out. And they connected this to some other research too, right?
Yeah, they mentioned a 2024 study by Ni and others, which also pointed to these strong nonlinearities introduced by ln, and suggested they might be helping the model represent more complex patterns in the data. They even made a connection to biological neurons, the whole idea of saturation, how neurons become less responsive to really strong signals. It's a pretty cool parallel.
So we've got this per element linear transformation, but with an overall non-linear squashing of the outliers. Can we unpack that a bit more? How does ln pull that off?
Check out figure 4, those left panels. It's all there. When you color code the points by token, you can see that, yeah, all the points for a single token, they do form a straight line when you plot input versus output. But here's the catch. Each token has its own variance, right? A measure of how spread out its values are. So the slopes of those lines, they're going to be different for different tokens.
Yeah.
Tokens with a narrow range of values, smaller variance, they end up with a steeper slope after normalization. Put all those token-specific lines together, and there's your S-shaped curve, your taunt-like behavior.
Got it. It's the mix of all those different straight lines, each with its own slope, that creates that overall curve. What about looking at it from the channel perspective?
Look at the right panels of figure 4. You'll see different channels. They often have vastly different ranges of input values. And here's the kicker. Only a few channels have those crazy extreme values we talked about. And those are the ones getting the most squashed. The channels with more moderate values, they go through more linear transformation.
Okay. That paints a much clearer picture of what's going on inside those normalization layers. Now let's get back to Dynamic Tanh dyt. The formula, again, is dytx plus x. We talked about the Tanh part, mimicking those S-curves. But what about that learnable scalar parameter?
Alpha, that's the secret sauce. It lets dyt adjust the scaling of the input values, and it does it dynamically based on their overall range. It's like mimicking that scaling that happens naturally in ln. That's why it's called Dynamic Tanh.
And we still have dec and bov in the formula. Those are learnable too, but they're per channel vectors, just like in regular normalization.
Exactly. Same job, really. They let the output of the dyt layer be scaled and shifted to the right range for whatever comes next in the network. They're considered part of the whole dyt layer, just like those parameters are usually part of a normalization layer.
So how do you actually use dyt? Seems pretty straightforward. Just swap out the normalization layers, right?
Pretty much. Look at figure 1 in the paper. It shows you visually. You've got a transformer block with an ln or RMS norm layer. Just replace it with dyt. Simple as that. Do this in the attention mechanisms, in the feed-forward networks, even in the final normalization layer of the whole transformer. Importantly, they didn't touch the other activation functions, things like GLU or ReLU. Everything else stays the same.
What about initialization? How do they set up AR and R at the beginning of training?
R usually starts as all ones, as all zeros. Pretty standard practice. For I, they found a default value of 0.5, Works well for most cases, except for those super huge language models. We'll get to those in a bit.
So the key point, even though it looks pretty simple, DYT isn't just another new type of normalization in the traditional sense. It's element-wise, it doesn't calculate any overall statistics.
Exactly. Each input element is treated individually. But here's the remarkable thing. It still manages to replicate that key behavior of normalization, squashing those extreme values while leaving the more typical values relatively untouched.
Okay, let's dive into the results. They tested this thing on a whole bunch of different models and tasks. What about supervised learning in computer vision? Using VIT and ComNext on ImageNet 1K, what did they find?
So across those architectures, across different sizes, base and large versions, DYT either did slightly better, or at least as well as LN. Look at Table 1 in the paper, and if you check out Figure 5, the training loss curves, the way the DYT models learn, it was really similar to the LN models.
That's a great start. What about self-supervised learning in vision, using things like MAE and Dino?
More good news. Table 2 shows it. DYT consistently matched LN across the board, different methods, different model sizes. Seems like it's not just good for tasks with labeled data, but also for learning from unlabeled data.
And they also looked at diffusion models like DIT, those powerful image generators, right?
Yep, they tested on ImageNet 1K, and DYT either matched or even beat LN in terms of FID scores. Check out Table 3. Important detail. In DIT, the OAT and BAT parameters of the LN layers, they're used for conditioning the image generation based on the image class. The researchers, they kept that functionality in their DYT experiments, only replacing the core normalization operation itself.
Now for the big one, the one I'm sure a lot of folks are interested in. Large language models, things like Llama. Normalization is considered critical for these behemoths, and Llama specifically uses RMS norm. How did DYT handle that?
This is where things get really intriguing. They successfully pre-trained Llama models, sizes ranging from 7 billion parameters all the way up to 70 billion, using DYT instead of RMS norm. Tested them on the pile, that massive text data set. They did make a couple of tweaks in the DYT versions, added a learnable scaler after the initial embedding layer, and played around with the initial IBA value, which we'll come back to later. But the big takeaway, look at Table 4 and Figure 6, DYT was right up there with RMS norm, both in terms of training loss after a whopping 200 billion training tokens and zero-shot performance on 15 different language model evaluation tasks.
That's incredible, especially for such a simple swap. What about other areas like speech processing or DNA sequence modeling? Did they test those too?
They did. For speech, they used the Wave2Vec 2.0 model on LibreSpeech, and DYT's validation loss was comparable to LN. Table 5 shows that. And for DNA sequences, using Hyena DNA and Caduceus models on those genomic benchmarks, DYT again held its own against LN, according to Table 6. So across a whole bunch of different challenges, DYT seems to be a very viable alternative.
Okay, so the performance is definitely there. But what about efficiency? Is this simpler approach actually faster in practice, both for training and using these models?
Early signs point to yes. They benchmarked it on a Llama, the 7 billion parameter version, comparing RMS norm to DYT on an NVIDIA H100 GPU. Look at Table 7. DYT significantly reduced the computation time, both for inference, running the model, and for training, updating the model's parameters. It hints at DYT being a more efficient building block, potentially saving a lot of compute and energy down the line.
That's huge, especially as these models keep getting bigger and more complex. They also did some ablation studies, right? Basically removing or changing parts of DYT to see what happens. What did they learn about the importance of that tan function in the IO parameter?
So for tan, they tried swapping it out with other nonlinear functions that also squash values, like hard-tan and sigmoid. They even tried removing the nonlinearity altogether, just using the input directly, while keeping an. Results are in Table 8 and Figure 7. The big finding. You need that squashing nonlinearity for stable training. Get rid of it, and things go haywire. Among the different squashing functions, tan worked best, probably because it's smooth and centered around 0.
So nonlinearity is key. What about a PA? What happens when you mess with that?
Take it out, keep the squashing functions, performance drops across the board. See Table 9. That learnable scaling factor, it's doing important work. Seems like that dynamic scaling is essential for matching the performance of regular normalization.
And what about the actual values about during training? Did they notice anything interesting there?
Yeah, during training, they saw that closely tracks the inverse of the standard deviation of the activations. Left panel of Figure 8 shows this. It's like Ali is dynamically adjusting the scale of the inputs to the tan function, keeping the activations in check, contributing to stability. After training, the final order values, they were strongly correlated with the first of the input activations. That's in the right panel of Figure 8. And they noticed that deeper layers tended to have larger standard deviations and, as a result, different OR values compared to the earlier layers.
So it's like a global dynamic scaling factor, unlike LN, which does a per element scaling and shifting. But that also means L can't do that fine-grained squashing of individual outliers that LN does, right?
Exactly. RE keeps the overall scale in check, but it's probably the combination of that scaling and the tan squashing that together give you the benefits we use to attribute solely to LN.
They also compared DYT to some other methods that try to get rid of normalization, like fix-up and skip-init. How did it stack up against those?
DYT consistently outperformed those initialization-based methods and also weight normalization method called SRIPREM. All the results are in Table 10. They even did a proper learning rate search for all the methods to make sure the comparison was fair, and DYT still won. It's worth noting that those initialization methods, they needed much lower learning rates to avoid instability.
Now, about that initial value for I, they said 0.5 worked for most models, but for the really big language models, it was a bit more sensitive.
Right. For most models, the final performance wasn't that affected by the initial I, as long as it was within a reasonable range. Figure 9 shows that. Except for VITL, the large vision transformer. High initial I values sometimes caused problems there, but lowering the learning rate usually fixed it. In general, smaller initial I's meant more stable training, especially for bigger models or higher learning rates. And that default 0.5, it gave similar stability to using LN. You can see that in Figure 10.
Well, for the giant llama models, it was a different story.
Yeah, those were picky. Tuning the initial I made a big difference there. Larger models liked smaller initial values. And they found it helpful to start I-llama higher in the attention blocks and lower elsewhere, like in the feed-forward layers and the final output layer. Table 11 and Figure 11 have the details. Interestingly, the model width, how many computations it does in parallel, that mattered most for the optimal I. Depths, how many layers, barely made a difference. Basically, the wider the network, the more you had to fine-tune those initial I's. They think this might be because those massive language models are just so wide compared to other networks.
It's always fascinating how those huge models play by their own rules. Now, before we wrap up, they did mention a limitation of DYT, right?
Yeah, one thing they're still working on. DYT didn't do so well when they tried to directly replace batch normalization in those classic convolutional networks like ResNet 50 and VGG 19. Performance took a hit there. Table 15 shows the numbers. They think it might be because BN is used so much more heavily in those architectures, like after almost every weight layer. So for now, it seems DYT's sweet spot is definitely with transformers.
So to sum it all up, this research makes a pretty strong case that you don't necessarily need those traditional normalization layers and transformers. And this Dynamic Tanh, DYT, it's the key.
For sure. It's amazing how something so simple can replicate what we thought was so essential about normalization.
And the potential benefits, they're huge. Performance is there, efficiency is there, and maybe most importantly, it forces us to question something we thought was set in stone.
It really makes you think, doesn't it? If we can replace something as fundamental as normalization with something this elegant, what else might we be able to simplify?
Makes you wonder what other assumptions we're clinging to that might be holding us back. Could this lead to even more efficient models, maybe even models that are easier to understand? It's definitely something to keep in mind as we see what comes next in this field. This is a real shakeup, and the ripple effects could be huge.